Okay, good morning, everyone. I hope everyone's doing well this morning. And this video lesson is to cover the lesson for Wednesday from the original timetable. We're going to cover two lessons today. The first one is sound characteristics, and the second one is sound intensity. So let's start. I'll have a lot of animations for you today. I'm going to have actually the two parts of the screen, so you're going to actually see the PowerPoint, not in presentation mode because I want it to be big. So it's actually like just like this in the regular view mode, and then my picture on the side, just when I do the little demos and so on. Okay, so let's start. So today's lesson is the first lesson about a very specific kind of wave or a very specific kind of periodic behavior, which is sound. Okay, remember in grade 11 we do sound, in grade 12 we do another type of wave, but we do light. So let's start talking about sound. Okay, the most important thing, to understand about sound is that sound is always a longitudinal wave. Okay, so always remember that sound is never transverse. Sound is always longitudinal. And if you remember what longitudinal means the way the particles vibrate is the same way that the wave propagates or moves or appears to move in the medium. Remember, sound needs a medium. It needs a material or matter or a substance around it to actually what to carry the wave or to carry the energy disturbance through until it goes from the sound source, which is my mouth, all the way to your ear if you're standing in front of me. Okay, so remember, sound can never travel in vacuum, or it could never travel in space. That's what electromagnetic waves do. Sound needs a medium. The medium could be a gas. This is when we call it sound. The medium could be water or liquid. That's when we call it liquid waves. Or the medium could be solid, like the ground, for example, which is what we could call it ground waves, shock waves, or matter waves. So remember, sound needs a carrying or a conducting medium. Okay, so that's the first thing. The second thing is sound is always a longitudinal wave all the time. Okay, all right. So what exactly is sound? Well, sound needs what? A sound source. Okay, so the old philosophical question um, that if a tree falls in the woods and no one is around, would it produce a sound? So obviously, the reason this is a very well-known philosophical dilemma or kind of like like a riddle is that it depends how you define sound. Someone could define sound as something that someone else detects or hears. Well, we are physics people. We know that if no one is around it, it still produces a sound because we define sound not by who hears it or what hears it or what detects it, but actually by what makes it. And we know for a fact that if a tree falls and then hits the ground, it's going to shake the ground and the particles of the air so much that a wave or a disturbance of energy will actually move throughout that medium, the ground medium and the air medium. So, as physicists, we have to say, yes, it produces a sound, even though maybe there's not a living organism around to actually detect it. Okay, because sound to us is the energy disturbance of a medium. So, for sure, yes, it does. A philosopher might say, but who's there to hear it? We don't care. We know that it happened because of the shaking and the vibration of the energy throughout the medium, okay? Or the transfer of the energy through the medium all the way until it dies off. Who cares who hears it or not, okay? So let me show you basically what sound is with a few really interesting and good animations, okay? So you remember this animation from before a couple of days, I guess, before we went out for the holidays, is that this is basically a very perfect, although even a bit simplistic, but it's actually the most basic representation of sound. So imagine me speaking being this. I don't know if you see the prompt or my pen moving, but basically on the left side of the pipe. Okay, so this gray bar right here, moving back and forth, right and left, is basically my mouth doing what? Doing, giving energy or giving motion to the air particles around my mouth. Okay, because I am speaking on and on and on and on and on. I am basically doing what? Giving energy all the time. Now, here's what you need to know about the particles of air. The particles of air are not always moving very far away. By the way, air does travel very fast, very far, but the thing is, with the air density always colliding together, on average, they stay within the same what? Within the same range. Okay, so that means what? Air is basically kind of like layers, or basically a continuous medium around you. So when I'm talking right now, imagine you're standing in front of me, a few feet away from me. I am talking right now. What I'm doing effectively is that I'm giving the particles of air around my mouth right here, on my head, basically, energy. And that energy would actually what? Would actually make them vibrate a little bit more. Well, here's the thing, they vibrate, but there's another layer next to them. So basically, what that layer starts to vibrate as well, and the next layer vibrates as well, and so on and so forth. The major difference, listen carefully, the major difference between this picture right here, this pipe thing on the screen that you see right now, and me talking, is that you know that within a certain distance, after a while, the amplitude or the energy that I'm giving the air is gonna die off. You know that if, for example, if we're at the school right now and I'm standing by our classroom door, room 221, and you're standing at the other end of the hallway, like all the way near the auditorium, and I speak normally, I don't scream, I just speak normally, you know you're not going to hear me by the time the energy of sound or the energy of the wave gets to you, because it would have been sucked out by all the air and also the walls and the ground until it actually got to you. This picture right here in front of you in the on the screen is basically telling you, as you can see, that, oh, this wave is going to the right forever. It's never dying. Well, waves always die off because a mechanical wave means what? There is friction losses as it goes through a medium. So it basically dies off definitely after a while. Okay. But again, the idea of this picture right here is that basically this layer gives to this layer, and then this layer gives to this layer, and it just keeps going until it meets basically its complete, you know, absence, or sorry, termination by the time it moved a certain distance. That's what we call sound. By the way, every medium allows sound to travel a certain distance within it. Okay. So, for example, a solid medium allows the same waves, a wave of sound or sound wave, to travel a different distance in it than a liquid medium, than a gas medium, and even different gases allow it to travel a different distance, and so on and so forth. Okay. But eventually, all sound waves die at the end of some distance. Okay. All right, so that's one interesting animation about it. Here's another animation as well. I just want you here to focus on, as you probably can see if you look on the central side or the central part of this wave, and on the right side as well, like the middle of this right side, you can see a red line and a green line, okay? If you actually look at the red and green line, you see that they are moving 100%, but they're not moving away forever. They move and come back. They move and come back, which means what? They move to one extreme end, to another extreme end, and obviously, just like the pendulum we did for the lab, they have to pass. If you obviously, if you even by logic, if you move from one extreme to another extreme in the middle, you had to pass by what we call the central or the equilibrium or the neutral level or point. Okay, so that means air is always going to be around you. By the way, remember one thing, when you talk, you never drive the air away. Because remember, driving the air away creates vacuum around your mouth, and that actually doesn't happen, okay? Because the air moves so fast, the actual energy just goes, but the actual particles come back and forth, back and forth, back and forth, okay? So I just want to show you something interesting here. I'm going to play with this amplitude. Let me see if I can zoom in. Ah, yes, okay. So I'm going to play with this amplitude um, uh, range, or basically this amplitude slider right here. But I want you to see what's going to happen here. So I want you to focus now on the red bar, okay, or on the red line. Apparently, the red line goes right and left. On the left side, it makes it to the top, to the end of this capital A right here. So I'm basically marking how far it goes to the left, okay? So it goes as far as the capital A, and then on the left side, and on the right side it goes as far, I guess, as the small a. Look, as this, I'm gonna, I think there's a pause button, I guess. Oh yes, there's a pause button. So there we go. So yeah, so here it is. Here it is as far as it goes to the left. So you can see it's between the P and the A. And then here it goes almost to the A, okay? So I just want you to see what's gonna happen if I increase the amplitude. So I'm gonna increase it. So now let's see what happens here. Oh, see, now it actually went to the left even more. So it actually went to the P, and then it goes to the T almost on the right side. So as you can see, this sound waves are actually waves because they do have an amplitude, okay? And the amplitude of a wave of a sound wave is just how loudly do you scream? How loud do you scream? And I'm gonna make the amplitude now very small. And you can see now that the amplitude is very, very small now. It barely looks like it's moving, but it actually is moving. It actually is moving, but that's a very low amplitude or a very quiet sound. This is you whispering. This is you whispering. This is maybe you talking a bit louder. This is you maybe talking normally, and this is you screaming. So always remember, everyone, the amplitude of a sound wave is just, do you talk very loudly? Are you screaming? Or are you talking very quietly, almost whispering? Okay, so always remember that. Okay. Here's another very, very interesting animation, okay? So before we do that, let's actually read the next slide, okay? Now, what's important to understand about sound, which I guess kind of relates to that philosophical question of the tree falling in the woods, is that all living organisms that are able to actually hear sound always hear it differently. You don't even have to be a different living organism to detect sound differently. Even different humans with different ages and different basically and different auditory abilities hear or detect sound differently. Okay. However, in general, all humans with any range of hearing ability can only hear or can only detect, or basically think about this way: your auditory nerve is only fired up or excited or activated only when it receives sound that is either vibrating, like the air particles are vibrating at 20 hertz, like 20 cycles per second, or 20 pendulum back and forth cycles per second, all the way up to what? From 20 hertz all the way up to 20 kilohertz, or 20,000 hertz. So let me explain to you what that means. Imagine air to be a pendulum. Okay, so imagine the air layer near my mouth right now, or near my ear, I guess. I'm listening to someone talk, is a pendulum, and someone is talking, and they're making the pendulum right next to my ear vibrate or cycle or shake or oscillate. Remember, all of these words mean the same thing. Vibrate or oscillate only 20 times per second. Obviously, it's still, you might say that this, yeah, I can't do it that fast. But by the way, for air, that's very, very, very low. Remember, air particles are very small, very light, which means they can vibrate very quickly. Okay, but let's say that someone is talking at a sound frequency that's only shaking the sound, or sorry, the air particles or layer near my ear only at 20 hertz or 20 cycles per second. That is the minimum level of frequency for my auditory nerve, and my entire hearing mechanism to actually get fired up or activated, and actually even transmit, a hint of a sound. Okay, same thing. If someone is talking at a very high level of frequency, 20 kilohertz or 20,000 hertz, that will be the maximum level at being fired up to actually hear that sound. I'll give you a very interesting example, which is the perfect analogy to light. This is the exact same analogy to what? To us only seeing we talked about a few times in this physics course and even in grade 10 science. We us seeing. So now I'm talking about light, not sound. So I'm talking about my visual detection now, seeing only the visible spectrum or the visible range of the entire electromagnetic spectrum. So let me relate this to you in a different way. The low end of your hearing ability, the low end of your hearing ability is 20 hertz, is 20 hertz. This is exactly like saying the low end of my vision ability or seeing or sight ability is what is the color red. You cannot hear anything. Your ear will not be activated or fired up or excited when it hears a sound with a lower frequency than 20 hertz. Okay, it will not. Just in the same way that your eye will not be fired up or excited, the rods and cones in your eye, the ones that actually detect the photons that actually fall into it when light goes into your eye, is that your eye will not be activated if light lower than the frequency of red light falls into it. It's still going through, but guess what? Your eye is not responding. You're still saying, I'm not seeing anything. And that makes sense because remember, we cannot see infrared. Infrared is lower frequency than red color. We cannot see microwave. Whenever you actually heat something in a microwave, you do not see the microwaves, yet you know they're happening or they're actually taking place because the food is receiving that energy and getting hotter. And again, the same thing, you cannot see radio waves near radio towers because they have a very low frequency that does not excite your eye. Okay, same thing on the other end. Your ear will not be excited if a sound with a higher level of 20,000 hertz frequency falls into it. Just in the same way that your eye does not get excited or does not respond to any light falling into it that's higher than what, remember Roy G. Biv, that's higher than the frequency for violet light. Okay, which is basically meaning what, your eye, if there's a photon of violet light that falls into your eye, you will be able to see it. Well, guess what? If a photon with a higher frequency than the violet color frequency, your eye will not respond to it. And that's why you cannot see what, remember, you cannot see ultraviolet rays. You know they're there. We know they're there because they cause cancer, and they actually change DNA. They excite electrons way too much in your DNA that they strip them off, and then your DNA actually changes or gets basically mutations and aberrations. You cannot see ultraviolet. You cannot, or detect. I like to use the word detect because it kind of like makes your body a machine, which takes the sensation out, so it makes it really just a physics discussion, not a biology or a neuroscience discussion. So you cannot see ultraviolet. You cannot see X-rays. You know they work. You know they actually go through your body because you see the X-ray films and the bones and so on. And obviously you cannot see gamma rays, and we know they cause mega destruction. Okay, so remember, 20 hertz to 20 kilohertz for the ear is like red to violet for the what? For the eye. Okay, but here's the thing. That doesn't mean, just so you know, everyone, just remember, that doesn't mean that you're going to hear. You're not going to hear the 20 hertz sound and the 20 kilohertz sound effectively as the other sounds in between. Actually, no. They actually found out that the ear usually really, really perfectly responds and really gets the best reception of sound if the sound is between 1 kilohertz, so 1000 hertz, and 5.5 kilohertz or 5500 hertz. So what does this mean? It means that officially your ear will be excited with 20 all the way up to 20,000 hertz of vibration, frequency for the air. That doesn't mean that you hear it. But if they actually did connect electrodes to your ear and to your brain, and they actually did see that a certain part of your brain got activated when it reached 20, on all the way up to reaching 20,000. Okay, but the brain getting activated doesn't mean that you actually sensationally do hear a sound, but you do receive it You do register it, but you do not actually claim that I am hearing something. However, you start claiming that you hear something when the sound reaches 1000 hertz up to 550, sorry, I mean 5500 or 5500 hertz. This is the best detection range for most of what? For most of human ears. Obviously, some human ears are more sensitive, so that means what? They can actually detect lower than 1000 hertz. Maybe they can detect 900 hertz or 800 hertz. Like someone could actually, like for example, by the way, just so you know, when you get older, your ear becomes lesser responding to what? To sound wave. Basically, the well, your cartilage around your ear or of the ear gets more rigid, so its vibration or its shaking as a response to other waves gets dampened, like it's weaker. So that's why older people hear sounds differently than younger people, because the ear itself changes what changes the rigidity or basically the elasticity of its cartilage material, and that's why it becomes more rigid, so it doesn't vibrate as as well as it used to be when for the 20 or a 30-year old. Okay, how? So that means, for example, someone young could actually claim they hear something when the frequency is 900 or maybe 800 hertz. Someone older might have to wait until it hits the 1000 hertz mark to say, oh, I just heard the sound. Okay, and the same thing on the other end. Someone younger might claim that they're hearing something that actually has a frequency of 6000 hertz. However, an older person would say beyond 5500 hertz, I cannot say I am hearing anything. Okay, and that's basically it. So the best detection range usually is from 1000 hertz to what? To 5500 hertz, but the official full range officially covers 20 to 20,000. It's an easy number always to remember: 20 to 20,000, 20 to 20 kilo. Okay, so because we are the most special species, I guess, on Earth, we we've divided or we've classified or categorized sound into three categories according to our ability to what? To hear or detect it. By the way, bats hear different frequencies. Dogs, we all know this. Dogs hear, the silent whistles. You whistle through it, you don't hear anything, but the dog goes insane because it's actually what equipped with with more detection range than our own, and so on and so forth. And different animals again see different colors or see different electromagnetic waves than actually we could do. They don't see it. I like to always hear the word, or use the word detect. Detect. Okay. So as humans, we've classified sounds into three ranges. Okay. The range that we hear, the range that we, the range that we can officially detect. So anything from 20 hertz to 20,000 hertz, 20 hertz to 20,000 hertz, or 20 cycles per second to 20,000 cycles per second of vibrational frequency. This is called the what? This is called the audible. Audible from auditory, from audio. So basically, this is the audible range. Okay, so any sound vibrating between 20,000 hertz, 20 hertz and 20,000 hertz. Anything vibrating lower than that, so obviously anything vibrating lower than 20 hertz, so 20 all the way down to zero, so no vibration whatsoever, like absolutely no shaking of the air particles, which honestly means no sound. Like I'm standing there in silence. I am not producing any energy to the air. That's called what? That's called infra. Infra. Remember, infra in Latin means below. That's why some people call it subsonic. So sometimes it's called sub. Sub means below, like sub-zero. Sub-zero temperature means below zero temperature. So subsonic. Okay. So subsonic, by the way, the word sonic is coming from the words sonography, okay, ultrasonic, infrasonic, so it comes from sound. Okay, it's the Greek word for sound. Okay, so, sorry, Latin word for sound. So infrasonic means something below your range, so something lesser than 20 hertz all the way to zero. So it's only this very small part here. And then we've got the other extreme, which is basically what? Which is basically ultrasonic, or now we know it to be supersonic. Infra and ultra, like infrared and ultraviolet. And those are two pairs. The other pair is sub and super. Subsonic, supersonic. Okay, so like these basketball teams, the Seattle Supersonics. Okay, so supersonic means what? It is vibrating. Let me take this one here. It's vibrating at more than 20,000 hertz of vibrational what? Of vibrational frequency ability. Okay, so it's really important to notice. So let me now show you a very interesting, what you call it, a very interesting animation or simulation that will really drive this to point. So if you can see this, there are two bars I could play with here. One for what? One for right here. One for the frequency. So I can play with this from 20 hertz, as you probably can suspect, all the way up to 20,000 hertz. Okay. Now you might ask, why am I not hearing anything? I mean, I claimed that we can hear anything officially from 20 to 20,000, and even our best detection would happen between 1,000 and 5,500. Then how come we're not hearing anything, even though now I'm in the good range? You see, remember, 1,000 all the way up to 5,500. This is the range where my detection should be best, prime, perfect. I'm not hearing anything for a very simple reason. My volume is at its lowest. So that's why basically nothing could be heard because the volume is zero. Okay, you're not even talking. Okay, so let's increase the volume. So you might say, what's going on? I'm not hearing anything. Of course, you're not hearing anything. Even though the volume is at the highest level, even though the volume is at the highest level, so sound is being produced, but your ear is not being fired up. Why? You are at the low range of what? You are at the very low range of the what? Of the sound. So that's why you are not detecting it. It's there, it's being made. Your ear is just not registering it. And I could do the other opposite way. I could make the volume zero and then go all the way to 20,000. Guess what? If I crank up the volume all the way, you're not hearing anything. I am sitting next to my laptop. I'm not hearing anything. Why? Because my ear cannot detect it. The air, by the way, just so you know, the computer now is producing through the speakers a sound wave now around the computer, around my laptop. It is making the air vibrate more than, sorry, 20,000, I guess, hertz or 20,000 cycles per second. And that's why my ear is not hearing it. But now let's actually what? I'm going to lower the volume a little bit so it doesn't get way too loud. Okay. And now check this out. I'm going to actually lower the volume and I want you to listen carefully. I hope you can actually hear the system audio through this presentation. It's, if you didn't hear it, I will provide the link and you should really play with this simulation because it will make you perfectly understand the difference between volume and frequency. They are completely independent. You could have a high of one and a low of one, and completely opposite if you flip them around. So, for example, let me give you an example here. The volume here is decent. It's somewhere here. So I'm gonna play with the volume. Sorry, with the frequency now. So the frequency now is 358 hertz. Okay. Now, obviously, think about this way. It would be not really the best comfortable experience to sleep to this, but you could definitely sleep to 200 because it's what? It's not as high frequency or what we call pitch. Anyone here who's doing music knows that pitch and frequency are basically what? Related because the pitch of the sound is caused by how much the frequency is what is being the frequency of the air particles around it. So let's crank up the frequency. Oh, now it's getting definitely more annoying because it's getting a higher pitch. It's like a high, that's what I call a high pitch scream. Okay? That's it. But guess what? it's now getting less detectable in my, like according to my ear. I'm starting to hear less and less of it, even though the frequency is going up. But my ear is what is becoming less efficient at detecting it. And I think I stop, see, my ear is stopping to hear anything around 15,000. And now obviously I am completely not detecting anything. So remember everyone, the volume is the height of the wave or the amplitude, and the frequency obviously is what? Let me just play this. The frequency is what is just the the basically like how compressed or how. So actually in this case, frequency is very related to the wavelength. Okay. So this is an amazing website. I'll send you the links for sure. I'll put them in in the in the PowerPoint presentation, so you could really play with it, even understand it more. Let me show you another one. So here, this is just an application or sorry, an animation or simulation of how sound is really made. So a tuning fork, I'm pretty sure some of you have seen tuning forks before. It's literally just like a fork that you basically what that you hit, so it vibrates and basically shakes the air around it. Okay, so I'm gonna run. So I want you to see what's going on here. So it's I want you to see how kind of like the air particles are kind of stuck to the to the two prongs or to the two ends of the tuning fork. That's more of a reason to believe that the air is not really traveling very far and very, it's still coming back. But here's what I'm going to do right now. By the way, this wave is still propagating all the way to the ends of this grid right here. And I'm going to prove it to you by increasing the frequency so you could actually see. And now you can actually, let me just get this one up here. You can actually see this is literally, by the way, that's why they always relate they always relate sound waves to a wave that is made by dropping like a little pebble or a little rock in a what in a pond, because the waves just basically go as circles or spheres, I guess. Well, circles if it's two-dimensional plane, I guess, like a surface wave. But in actual real life, it actually goes like a sphere, a full sphere all the way to the outside, outward sphere. Okay, you can actually see that how it's basically literally like the center of it is right here, and then the waves, just like water waves, are just going out and out and out and out. Okay, you can actually click here basic motion of air molecules, because obviously molecules are never just standing still waiting for a tuning fork, they actually vibrate. So but this makes it then harder to see the circles when they actually expand out. Okay, so that's why I took them out of the whole thing, just to simplify the animation a little bit. Okay, here's another animation, same thing. I will show you. See, there's a frequency. I don't know if you can see this. There's a there's a frequency and an amplitude. So again, remember, if the frequency is very low or very high, we might not be able to hear anything. Same thing, if the amplitude is very low, that means you're not talking, you're not even whispering. Amplitude is very high, that means you're screaming. But even if you're screaming at a very high frequency, your ear might not be able to detect it. I'm gonna prove it to you. I'm gonna first here, I'm gonna stop it, I'm gonna pause it. I'm gonna increase by the way, this is not the 20 to 20,000, so you will still hear a sound, okay? But I'm going to make them here, and then now I want you to just, see what's going to happen here. Look at everyone, look at the diaphragm, or basically this little membrane, the beige membrane, vibrating. You see how it's vibrating a lot, like it's almost touching the actual tube itself. Well, look what's going to happen when I make the amplitude less and less and less. I don't know if you can hear the sound coming from the speakers. The sound is basically dying off. And see, it's actually the membrane, it's not moving. I'm gonna move it a little bit. I'm gonna make it, see, the membrane now is what is shaking. And now I could even make it, if I, you see, the frequency is going lower, which means the sound is getting more soothing, more soothing. Okay, so everyone, let me give you basically, four possible cases here. So I just want you to listen very carefully. So remember, probably the most two important features of sound are its frequency and its amplitude, or its frequency or pitch and its amplitude or loudness. Okay, so here are four possible things, or four possible cases you can have. Why? Because each one of those two, each one of the frequency and amplitude, could be high or could be low. So let me I give you actually four examples here. So example number one, just focus. It's very simple. I'm going to act out the whole thing for you. So the first one is what is low frequency, low volume. So low frequency, which means low pitch, and low volume, which means low amplitude. This is basically you going like this. Like, for example, I am so low frequency means I cannot shriek, I cannot be very high pitched, I have to be very deep voice. So like what? Like, for example, slow singing, or an opera singer. They have very, they never they scream, but their vocal cords are not vibrating very, 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 very quickly. They're vibrating, well, they're quickly, but not as quickly as when someone has a very high pitched voice. So, for example, low frequency and low amplitude is like this. Oh, see, it's my voice is deep. Deep, by the way, deep voices mean low frequency. Okay, deep voices means low frequency. So because my voice is oh, my voice is deep, which means low frequency, and I wasn't screaming. So that was what? Low amplitude. Okay, I'm gonna now keep my frequency low, so I'm gonna keep my voice deep, but I'm gonna up my amplitude. So basically that just means I need to scream. Okay, so instead of going oh, I have to go oh. So now it's the same voice level, okay, or the same octave. Those of you who are doing music, it's the same octave, but it's a higher. I basically just went with the dial of volume, and I just, cranked up the volume. Okay, I tuned it up. Okay, so those are two cases where the frequency was kept low and we played with the amplitude. I basically screamed, or basically got louder. Okay, so now I'm going to do the opposite. So let's now do what? Instead of low frequency, high amplitude, I'm going to go high frequency, low amplitude. So you're telling me that I have to, because it's low amplitude, I cannot scream. I can only whisper, okay? Or be very quiet. But I can be very what? Very high pitch. So here's one, okay? This is high frequency, low volume. I could do this. Zzz, like a bee or a fly buzzing around you, which is insanely annoying, not because it's loud, it's because it's high pitch. So again, I am vibrating my teeth at a very high rate, but I'm vibrating it with a very low frequency, sorry, with a very low amplitude. Now I'm gonna make both of them high, which is the other extreme. Okay, so I'm gonna make high frequency and high amplitude. That means you're telling me to still do a buzzing sound with my teeth, but I need to really, really what? Make it very loud. So it would be instead of just zzz, it's now zzz. I'm still vibrating my teeth at the same rate, but now I give more energy to the what? More energy to the air particles, and that's why it's a higher volume. Okay, think about this way. If I'm standing by the classroom door and I just do this, if you're standing by the auditorium, you're not going to hear it, because the energy is so low. By the time it made it maybe to like maybe halfway through the hallway, it would have died. But if I do this, you're probably going to hear me, which means what? You are going to hear the remaining energy that basically was able to survive and travel all the way to the auditorium. So remember, four different cases. You can have low volume, sorry, I like to start with frequency first. You can have low frequency, low volume. You can have low frequency, high volume. You can have high frequency, low volume, and you can have high frequency, high volume. Okay, all of them are completely unrelated, and because they're unrelated, you can produce these four cases. Okay, that hopefully should make so much sense, hopefully, about waves of sound and how they actually produced, and what those terms now mean in this unit so far. Okay, so this is technically the sound characteristics. Okay, this is the properties of sound. The rest of the lesson is going to be for sound intensity, or basically how loud the sound could get. Okay,